Please title these notes Integrals 9 Notes, Tricky Sums, and write today's date.
By the end of this lesson, you should be able to use Riemann sums in not straightforward problems. The first thing we're going to need for this lesson is we're going to need to really know well our underestimating versus overestimating charts. So right here where you have the left sum and the right sum, increasing, decreasing, try to fill in from memory what situations the left sum overestimates versus underestimates, and same for the right sum. Do the same thing with the trapezoidal sum as well. So take a second, try to fill that in. So here's what you should have. So increasing, remember, is this, decreasing is this. And if we have a left sum, that means the left sum is the left side of the rectangle is touching. A left side of the rectangle is touching. For the right sum, the right side of the rectangle is touching. And we can see from drawing that this underestimates, this overestimates, overestimates, and underestimates. For the trapezoidal sum, increasing, decreasing doesn't matter, but for concave up, whoops, wrong color, concave up, trapezoidal sum overestimates. And for concave down, trapezoidal sum underestimates. So those things are really important to know for problems like this one.
Please title
For problems like this one. The function f is defined on the interval from -3 to 4. F of x is continuous and differentiable on this interval. This just means we never lift our pencil. This just means there's no sharp turns, there's no points where there's a vertical tangent line, and we know that f of x always is less than 0, meaning f of x is always negative or below the x-axis. If a left Riemann sum overestimates the integral of f of x from -3 to 4, and a trapezoidal sum underestimates the integral from -3 to 4, sketch a possible graph of f of x and justify your reasoning. Now, in the past we've worked with determining underestimates and overestimates when given a graph. Now we're turning that on our head. Now we know something about overestimating and underestimating, and we're saying what can we conclude about the curve. So for each thing we're told, our reasoning is to translate that into something about the curve. Is it increasing? Is it decreasing? Is it concave up, concave down? So here's our reasoning. The first thing that we can say is if f of x is less than 0, then f of x is below the x-axis. It's negative, that's all. We're also told that a left sum if a left sum overestimates, that means f of x must be decreasing. And if we're told a trapezoidal sum underestimates, over here, f of x must be concave down. So what we want to do is we want to sketch a graph and we want to go from -3 to 4, because we don't know anything about what happens beyond that. and we want f of x to be below the x-axis, decreasing, and concave down. So that means going from -3 to 4 should stay below, be going down, and be curved down. Something like that. And that's all there is to it. So that's one sort of strange problem we can see. Here's another type. In previous lessons, we've been given values in a table and then used those values to estimate the integral of a function. In this problem, we're going to be given the value of the estimate, and then we're going to have to find something else, going backwards in a sense. So this problem says the function f is continuous on the closed interval from 3 to 9, so those brackets just mean including 3, including 9, and it has the values given in the table below. So right down here, when x is 3, f of x is 11, so on. The trapezoidal approximation of the integral from 3 to 9 of f of x dx, found with the values in the table, is 24. What's the value of k? And notice there's a k right here instead of these numbers. So what we're going to do is we're just going to set this up as if we were using these numbers to find the trapezoidal approximation. But we're not going to be able to find that number because of k. We're told, however, what the final answer is, so we're just going to have to solve backwards. Try to give this a shot. See if you can get anywhere on your own before watching me do the problem. So what I'm going to look at is I know that when I'm doing my trapezoidal approximation, basically I've got this little sort of graph here. These are all positive, so I can go up here. So 3, 5, 7, 9. And I know that f of x is 11, 6, don't know what it is here, and 2. You don't have to draw this little chart, I just find it helpful. So to do my trapezoidal approximation right here, what I'm going to do is I'm going to do this height plus this height divided by 2, and then times this width here, which from 3 to 5, we just go over 2. So each of these is giving me the height. So I know this height is 11, this height is 6. So my trapezoidal sum is going to be 11 plus 6 over 2, the average of those heights, times the width, which is 2. And now I can just do that same thing for each of these. Each of these is the height of one of the parts of the trapezoid. So we're at 11 plus 6 divided by 2. Now I'm going to find the average of these heights. If this height is k, I don't know what it is, 6 plus k over 2 times 2 plus from k to 2 times 2. Now I'm told that this estimate is 24. So I can say 24, and this is the estimate, so I can say it equals this. We can cancel out these 2's, or if we couldn't cancel them out, we could just distribute it and divide. So we've got 11 plus 6 plus 6 plus k plus 2. Now all we have to do is combine like terms and solve. So 11 plus 6 plus 6 plus 2, 25 plus 2k, subtract 25 from both sides, divide by 2. There we go. Notice that my sketch over here was in fact entirely inaccurate. This point is actually here below the x-axis, but that's okay because I was just drawing a little sketch in order to help me figure out how to write this formula. So that concludes Integrals 3 Notes.